on I-open sets. Perhaps the most fundamental concept of general topology is the notion of open set. And in fact, each topological space can be considered as a universe X with a family of open sets. And this family is topology. We may also speak about closed sets, which are complements of the open ones. If A is open, then the complement of A is closed. The notion of openness, and the same with the notion of closeness, is directly or indirectly associated with many other topological concepts, like continuity, compactness, density, Unoue density. As we know, the set A contained in X is open with respect to the topology tau in X if and only if it's identical with its interior, and this interior is the union of all open sets contained in A, or equivalently, the biggest open set in terms of inclusion contained in A. Of course, we also know the notion of closure, where closure is the intersection of all closed sets in which A is contained, or equivalently, the smallest closed set in which A is contained. Now it should be known that topologists have introduced many weaker or generalized forms of open sets. Among the most popular families, we have alpha open sets based on the idea that A should be contained in interior of closure of interior of A. Semi-open sets, A is contained in closure of interior of itself. Pre-open sets, A is contained in interior of closure of A. And beta open sets, A is contained in closure of interior of closure of A. And all these families are associated with certain generalizations of the notion of interior. We have alpha interior, sigma interior, pre-interior, and beta interior. And the same with closure. Yes, some weaker forms or generalized forms of closure, like alpha closure, sigma closure, pre-closure, and beta closure. And of course, also the notions of alpha continuity, semi-continuity, pre-continuity, and beta continuity have been extensively studied. There are also other concepts. There are many such concepts. For example, among many, we have B open sets introduced by Andreevich, star B open sets, or B hash open sets where A should be equal to the union of closure of interior of A and interior of closure of A. This idea has been studied by Parameswari and Tagavel. And in this presentation, we shall demonstrate the very idea of so-called I-open sets. Small I here, not capital I, small I. They've been introduced by Amir Mohammed and Sabi Askandar in 2012. A few years later, in 2019, Mohammed and Beida Abdullah presented an extension of this concept, so-called II open sets, and we shall describe them in one of the next videos, maybe. So this part of our presentation is strictly based on the articles by Mohammed and Askandar. And also all the examples are taken from their articles. However, we have discussed them, we shall discuss them in a more detailed manner. We shall describe and point out some subtle problems. We say that a subset A of a topological space is I-open if there exists an open set G, which is different than an empty set and different than the whole universe, such that A is contained in closure of A and G. Yes, we calculate intersection of A and G and its closure, and then A should be contained in this closure. The complement of an I-open set is called I-closed set, of course. Well, some examples. Consider the following topology on the set ABC. Empty set, the whole universe, and the open sets are also singleton of A, and AC. And now these are the I-open sets. For example, consider AB. In this case, our G is AC because AC is open, it belongs to topology tau. AC is different than empty set, different than X, and it's contained in, and AB is contained in a closure of the intersection of itself, of AB and AC. This intersection is a singleton of A, it's here, but all the closed sets in this topology, the only closed sets in this topology are empty set X, BC, and B. And from this you can conclude, you can infer that the closure of A, the smallest closed set in which A is contained, is just the whole space X. Moreover, as you can see, and of course AB is contained in X, this is obvious. As you can see, closed set, even different than empty set and X, can be I-open. Closed set can be I-open. This is the case of BC, for example. Yes, BC as a complement of A, it's closed because singleton of A is open. And at the same time, BC is on our list of I-open sets. Here we have another topology on the set, on the universe which contains three elements, DEF. Here's our topology. And now the I-open sets are these ones. Note that, for example, singleton of F is not I-open. Its intersections with open sets different than X and empty set are F and D is equal to F and E is equal to F and DE, and these intersections are empty. All these intersections are empty. And the closure of the empty set is empty set. But, of course, singleton of A is not contained in the empty set. Yes, nothing is contained in empty set. Only the empty set itself. Yeah. Yes, because this is our condition, that A should be contained in the closure of A and G, where G is an open set, and so on. One can prove that every open set in a given topological space is I-open, but the converse is not true, as the following counterexample shows. Yes. This set GH is I-open because of this fact, but it's not open, yes, it's not in our topology. We can prove that every closed set is I-closed, that every semi-open set is I-open, and that every alpha open set is I-open. Now assume that X with tau is a topological space. Then we say that tau I, with superscript I, is the family of all I-open subsets on X. We call it I extension of X tau, or I extension of tau. However, this extension need not to be a topological space. If it is, then we say that X tau is topologically extended for I-open sets. That is TEI, TEI. Otherwise, it's called non-TEI. And the following theorem holds: if X is a non-empty finite set, and our topology contains only empty set, the whole universe, and the singleton of certain element, A is a singleton, its cardinality is 1, then X with topology tau is TEI. So the family of I-open sets associated with this topology will be a topology. Will also form a topology. Well, and the whole theory of I-open sets has already flourished, and maybe it will be studied in our future videos. These sets are investigated mostly by their inventors, by Mohammed and, as you can see here, Askandar, but not only by them. And for example, the following notions and concepts have been extensively, studied, maybe not introduced, yes, my mistake, have been extensively studied, introduced and then studied. I-continuity, I-separation actions, I-open sets in bitopological spaces, and soft I open sets in soft topological spaces. Yes, soft sets are certain generalization of the very idea of fuzzy set, yes, in some sense. And this is our bibliography. As you can see, indeed, we have I open sets in bitopological spaces, I soft separation actions in soft topological spaces, and I separation actions, for example. Thank you very much for your attention.